Now I'll talk about a few more things about this formula, this Newton's law of gravitation. So far I've explained how we can use it to find the force between Earth, which is really huge, between Earth and a little ball, which is some distance away. Okay, and when we do that, the numbers that we must use are the masses, which is let's say m1 is the mass of the Earth, m2 is the mass of the ball, and we also need r, the distance. And specifically, to be precise, this distance is the distance from the center of the Earth to the center of the ball. So that's the exact distance that we're talking about, not from the surface of the Earth, but from the center. So once we have these numbers, we know how to use this formula to calculate the force of attraction between them. And of course, we mustn't forget that Newton's third law, that if the Earth attracts the ball must also attract the Earth, right? Even though it doesn't feel like there's a force on the Earth because it doesn't move since it's so massive. Okay, so we are here now. This formula, right, the important point to mention about this formula is that it doesn't just apply to the Earth and this ball. It applies to any two masses. Okay. So this formula, if I have, let's say, two masses, m1 and m2. Let's say I have a stone. Okay, let's say this is a stone that I hold in my left hand, and this is a ball that I hold in my right hand. Just two little objects in my two hands. Now, even in this very simple situation, there would be a gravitational attraction between this stone and this ball. It's hard to imagine because these two forces would be so small. It would be so small. If you try to calculate them, you can try and think of some values, like maybe the stone is 0.2 kilogram and the mass is 0.1 kilogram, and let's say the distance between them, between my two hands, well, maybe 0.5 meter. Okay, so that's my r here, and g, we know what g is. We can look that up, and that's 6.67 times 10 to the minus 11, okay, in SI units. So that's a very small number, and if you put these numbers into there, then because of this very small 10 to the minus 11, you expect the force to be very small, maybe also about 10 to the minus 11 over Newton. Very small force, and we are never going to feel it, right? Not in our hands. Our hands are used to lifting kilograms of weights. So, but it's there nevertheless, and if we have some extremely sensitive and accurate instruments, we would be able to measure this. And okay. So this is one thing about Newton's law. It applies to any two masses. So this is one important point. Now the other important point about Newton's law of gravitation, about this formula, is that to be precise, it is actually defined. All right, it is actually defined for 2 point masses. Right, to be precise, this formula is true when you have two masses which are points. What do I mean by point masses? Point masses just mean masses that are extremely small, so small that the size is 0. Now, of course, that's completely theoretical. All right, we won't have something with mass like maybe 1 kilogram or half a kilogram mass, that we won't have an object that has a 0 size. Though maybe you can say that an electron might have a 0 size, but that's because people have never been able to measure it since it's that small. Or you can say that a black hole has 0 size because it sucks in everything and collapses into a point, but we'll never know. Okay, so in any case, maybe there are such things, maybe not. But theoretically, if we imagine that it is possible to have two masses with 0 size, then this formula is actually defined for this situation. Right? I've not mentioned this before, but this formula is actually defined for this situation, and it will give the correct force exactly for this situation when I have 2 point masses. So if you like, that's the starting point of this law, right? Separated by the distance r. Okay. That's the starting point of the two laws. But we can actually, it can be proven mathematically that this formula is also exactly correct if I have a situation where I have two circular masses. This is a circle, this is another circle, can be of different size, but spherical masses, right? Spherical masses. It can be proven mathematically that starting from this definition of the law based on point masses, if I have spherical masses, they must be uniform, of course. I cannot have like one side heavier than the other. Right? Uniform circular spherical masses. Then the law is still exactly correct if I take my radius from the centers of the two spheres. Okay, then the law, this formula would also give me the correct force between the two masses. So we need to be clear about the situation where this equation works correctly. Okay. Now we come to the real life. We come to a real life situation. Now there are two real life situations that we need to know about. Okay. The real life situation, what if I have an irregular object? What if I don't have a ball, but I have a piece of rock, all right, of a irregular shape. So I have the earth, I still have the earth here, and I have a lump of rock, right, some irregular shape, rock. I have with a mass m2 as well, like my ball, same mass but odd shaped. Can I still use this? Well, I can with some reservations. Now, what are the reservations? Okay, so first of all, it is in order to still be able to use this reasonably, or maybe approximately, the size of my rock must be a lot smaller. All right, a lot smaller than the distance between the center of the earth and the rock. Now, that is, if you're talking about distance if you're talking about attraction by the earth, distance is almost never a problem, because the distance from the center of the earth to any object that we can hold in our hand on earth is huge. Right, we're talking about 640 or so, 6,400 kilometers radius compared to the size of our hand, which is a few centimeters. So as long as the distance is huge, as long as the distance r is much larger than the size of the rock, okay, then, or the size of the masses of, I'll call it m1, m2, of the two masses, then I can also use this law, even if it is irregular. Okay, so as long as the distance between the two masses are large, compared with this funny symbol here with the two more than sign means a lot larger than. As long as the distance in between is a lot larger than the sizes of the two masses, then the formula would be approximately correct. This is my formula. This is my law. Okay, law. So the law will be approximately correct. Okay, so I can still use it to some reasonable accuracy. Now, finally, not finally as in all cases, but for what I want to talk about, this last thing is about coming back to the Earth itself. Okay, coming back to the Earth itself. Imagine another situation where instead of lifting the ball above the ground, what if I dig a hole? What if I dig a hole into the ground and bring the ball underground? Okay, so this situation is about underground. Now, if I go underground, that means that I go closer to the center of the Earth. Surely, well, that would mean that my distance r becomes smaller as I dig a hole and go into the ground with my ball. So if I go into the ground, I get closer to the center of the Earth, so r becomes smaller. Now, if I divide by a smaller number, I will get a bigger answer, right? So does this mean that if I go into the ground, if I go underground, does this mean that I'll become heavier, that I'll experience more attraction from the Earth? The answer is actually no, because if I dig a hole, okay, if I dig a hole and if I go into the ground, if I'm here, although I'm closer to the center of the Earth and in theory the r becomes smaller and this equation seems to become larger, but I must not forget one thing. If I'm underground, then above me there would be all the soil above me, all right, all the earth that is above me, and those have mass and those would also attract me. So when I go underground, I would start getting gravitational attraction from the ground above me, and that would cancel off the attraction from the Earth below me. Not only that, as I go underground, there would be less Earth below me now, right? Because some of the Earth are now above me, and this means that I also have less attraction towards the center. So going underground actually means that the gravity would decrease. And in the extreme case where if that's ever possible, if I actually dig a hole all the way to the center of the Earth, and if I stand at the center of the Earth, then what do you think the weight will be? If you're at the center of the Earth, right? If I'm right there, if I'm at the center of the Earth, it doesn't mean that r is 0 and I have number divided by 0 and therefore I get an infinite answer. Because if I'm at the center of the Earth, I'm surrounded by the Earth, so I get attraction on all directions from the Earth around me, and this means that the resultant force is 0.